Okay, hello, welcome everyone to this video on SpiceSharp Fluid Flow Solvers. So just a few things. You will be able to find some useful links within the description box, including my GitHub repository right here, which I will put the documentation and everything here, including discussions on my YouTube videos. So actually, since the last video, I already did some notes for you. Okay, also for myself mostly, that there's a good analogy, somewhat nice analogy between electrical circuits and flow circuits, fluid flow circuits. However, of course, in flow resistance there are lots of non-linearities, and that's because we have a very non-linear relation between the friction factor and pressure drop. Okay, or rather a non-linear relation between fluid flow rate and pressure drop. Okay, you see the friction factor here is actually some very complicated equation, a very non-linear equation, and of course you have a u squared term right here. Okay, so this is the deal with fluid flow. Okay, of course, last thing I want to do is that yes, I'm taking note of this license by MIT license for SpiceSharp. Okay, the permission is hereby granted free of charge to any person obtaining a copy of the software and associated documented files to deal in the software without restriction, without limitation in rights to use, copy, modify, merge, publish, distribute, sublicense, and or sell copies of the software, and to permit persons to whom the software is furnished to do so, subject to the following conditions. The above copyright notice and this permission shall be included in all copies of substantial portions of software. So I will be using this MIT license, and I'll probably copy and paste bits of it. And I myself, since I will be using, I'll be sort of using this SpiceSharp Fluid Flow Solver as a derivative of the, what do you call that? Yeah, as a derivative of the SpiceSharp electrical circuit solver. I will also be using the MIT license, and I'll probably use the this copyright notice here as well. I'll need to put it in. Okay, so that's okay. Yeah, I should put it in here. It's gonna be a little bit of his stuff as well. So I'm gonna go to Vim license. Okay, insert and paste. Okay, and I think that's it. Save, quit. Okay, I'll git add. Yeah, so I will add this stage this for changes. I'll put the name down there just to make sure, yes, it belongs to him as well. Alright. Okay, so this is just some acknowledgement stuff, some administrative things, legal stuff that I need to do, all under MIT license. Okay, so let's continue where we left off. So last time I told you there is this very good analogy between electrical circuits and flow circuits. I put some notes here, and we find out that we actually need to deal with some nonlinear solvers. Okay, the nonlinear solver part will be, you can actually find it under SpiceSharp in the modified nodal analysis. Okay, and you can see that for this simple circuit right here with two current sources, three resistors here, you'll use Kirchhoff's current laws like 3 times, so that you will be able to solve these equations. Okay, so Kirchhoff's current laws states that the sum of currents in every node has to equal 0, meaning to say current in equals to current out. Okay, so where are the things taken? Well, you can take the current across this 5 ohm resistor. Okay, the current across this 5 ohm resistor will be well, you can see this V1 right here, this node right here. The current coming into this resistor is 1 ampere. The current coming out is actually V1 minus V2 over 5 ohms. Okay, so this is the node for V1 right here. So you take this node V1 as the so-called reference point. In comes 1 ampere, out goes V1 minus V2 over 5 ohms. That is by Ohm's law, I equals to V over R. Okay, and then do the same for V2 and V3. You will come up with these equations, and this is a very nice linear equation right here. Okay, modified nodal analysis is that if you don't have a current source and you got voltage source, you kind of do the same thing. Pretty much the same thing, except you put in the voltage as one of the unknowns on this column right here. Okay, so there are simultaneous equations which we can rewrite into matrices. Okay, and we can solve the matrices to find V1, V2, and V3. Yeah. So the 3x3 matrix on the left is called the admittance matrix, while the current vector on the right here, or vector on the right here, is called the current vector. Okay, so yeah, this is a modified nodal analysis where we have this sort of setup where we have unknown currents and voltages on this side, known currents and voltages on this side of the thing, and then the matrix equations, and the admittance matrix is whatever you see here. Alright, so we have matrices for linear components, but we know it doesn't really quite work for non-linear things. So what we need to do is to resort to this thing called the Newton Raphson method. Okay, now Newton Raphson method for multi components like this. You see this vector notation, fx equals to 0. There's Jacobian right here. All this can seem very confusing, so let's break it down. Okay, anyway, this is a very high level methodology. Let's break it down how this Newton Raphson thing works and how we use this to formulate our matrices. Okay, so the Newton Raphson part is just to formulate a proper matrix like this, and then after that SpiceSharp will have its own matrix solvers to go and do its thing. Okay, it will have its own matrix solvers to go and solve things out and do whatever it needs to do. Okay, so the tricky thing here is of course the Jacobian, which I will not touch just yet, but know that this is just a matrix of derivatives. Okay, and of course this can be pretty abstract right now, so let's take a look using some of this system. Yeah, I want to take a look at the Newton Raphson method using with reference to this Appendix A, solving systems of nonlinear equations. It's part of linkspringer.com. If you take a look at if you look at Newton Raphson method and you look for simultaneous equations on Google, this is one of the first things that actually popped up on mine. So this is a very useful document to help you understand what actually is going on right here. Okay, so I will not be referencing directly to this using this document, but just know that this is under power systems operation, power electronics and power systems. Okay, under Springer International Publishing. Is a copyrighted document. Go and read it yourself. I'm not going to go through in this video, but I will leave the link in the description. Okay, so let's talk about Newton Raphson method, and of course after that I will talk about matrices as well. Okay, we are going to use a lot of matrix notations. That's why I just leave a very blank matrix right here, which I can just copy and paste later on. Okay, so let's talk about Newton Raphson method for nonlinear equations. Alright, I'll just compile this, and the next thing of course is to sort of give you a sort of an overview. Okay, this is a pretty basic engineering knowledge, as in computational methods. Basic that is if you already graduated. If you have not graduated from undergrad, then it's not so basic. Okay, so yeah, this is usually a year 2 or year 3 course, but yeah, let's say you have I'll just give you the most basic example first of the Newton Raphson method. You have a y and x axis. You have some very weird function right here. Okay, y equals to some function of x. Y equals to f of x. How are we going to solve it? Okay, so how are we going to solve f y equals to 0? Okay, or rather f of x equals to 0. F of x equals to 0. This is actually what we want to solve for Newton Raphson method. Okay, so Newton Raphson method actually takes advantage of this. Okay, Newton Raphson method actually takes advantage of derivatives. So at the end of the day, we want to solve for this. Okay, or maybe I shall use the thing. We want to solve if we have some. Okay, let me put this as a section. What this will be a simple, one equation example of Newton Raphson. Okay, this is the one equation example. So I'm gonna go through all of this. If you already know this stuff, skip the video. Yeah, it's not for you. Okay. We want to solve if we have some equation y equals to f of x. Okay, I'm going to compile. Okay, let's do a quick build. Okay, we want to solve this equation. F of x equals to 0. Alright. Okay. Okay, let me get rid of some of these warnings first. Input encoding. Okay, now I'll do it later. Okay, so we want to solve this equation, f of x equals to 0. Okay, this is what we are solving right here. And we are actually going to make use of derivatives to help us get there. We are going to make use of derivatives to help us get there. That's the idea. How are we going to use the derivatives to help us get there? Okay, so we'll have these derivatives, fraction d by dx of fx. Okay, d by dx of fx, this will be equals to, this will be equals to f x I plus 1, or rather x plus delta x minus f of x divided by delta x. Okay, this is a first order Taylor series expansion. Okay, we do a first order Taylor series approximation of derivatives. Alright, we do a first order Taylor series expansion of derivatives. So this part should be quite intuitive, but how does this actually help us get here? And that is the thing. Okay, how does this help us get here? Okay, we want to make it such that okay, this value here, fx plus delta x, approximately equals to 0. Okay, we want to make it such that this fx plus delta x will fulfill this equation. It will solve this equation right here. Okay, so yeah, so we want to make it such that this fx plus delta x actually goes to 0 as far as possible. Okay, so it's approximately equals to 0, but not quite 0 just yet. Okay, should be as small a value as possible, and then we'll look for this delta x. Okay, so x is like a starting point. Okay, let's say you start out here. This will be your f of x. You can compute f of x as long as you have what f of x is. Alright, you have this f of x, and then what are you going to do? Right, you also have to compute this dfx dx. So you need to compute f prime of x here. You also need to compute this. Okay, so this thing right here will be the this will be the derivative. Okay, this will be the derivative f prime of x. Okay, so again, how do we connect this using these derivatives to help us find the root? Okay, we try to substitute this fx equals 0 over here, so that fx plus delta x is approximately 0. Okay, so okay, before I get ahead of myself, I want to substitute this back into the equation, so that fx plus delta x is approximately our solution here. So I'm going to put this, so we have this. Okay, we'll have this, this is maybe 0 plus or something like that. This is a bit more than 0. Okay, or maybe it's some error or something, some small error. Okay, and then we are going to multiply throughout by okay, maybe I would say this quantity is so small in comparison to this quantity, okay, that we can almost just ignore it. Okay, so I say fx is actually significantly greater than fx plus delta x. Okay, so because we have this going on, we can essentially just ignore this term. We can essentially just ignore this term. Alright, we ignore this term, and we sort of do solve for this equation. Okay, we solve for this equation to get our delta x. Okay, so we solve for this equation to get our delta x. So let's make this equation explicit in delta x. Okay, solve for delta x. So I'm going to make delta x the subject of the equation. So this is very much a very quick way of doing things. Okay, I solve for delta x such that okay, delta x equals to minus fx over dfx dx. So you see that solving for the delta x is actually pretty straightforward. Okay, once we have this thing going on here, okay, we can make fx the subject. Okay, make delta x the subject. We compute the fx and dfx dx. Right. So as long as we know fx and we can differentiate that, and that's of course the hard work actually, the differentiation part. Okay, as long as we have the differentiation, we are managed to differentiate it correctly, we will be able to find delta x. And once we find delta x, what can we do? Okay, once we solve for delta x, we can update. Okay, we can actually find the true value of f, okay, x maybe I plus 1 equals to fx plus delta x. Okay, and this is, of course, we hope that it gets to 0, but of course this is not truly 0, right? So fxi plus 1 equals to fx plus delta x. Okay, so this delta x is something we solve for, and then we update it to the next iteration of x, so that we get more closer and closer to 0. Now, what does this look like pictorially? Okay, I'm going through this very fast and I'm skipping a lot of intermediate explanation steps, but this is more or less what we are doing with the Newton Raphson method for one dimension anyway, right? We are computing this computing this derivative here. We're computing this derivative here. Okay, dfx dx, we are computing this derivative here. What is fx over here? Fx is over here, right? So, and what is fx plus delta x? Okay, fx plus delta x, well, if you look at this, this is actually the slope of the derivative. Okay, this is the slope of the derivative right here. This is the slope right here. Okay, so delta x will be, I guess, just this much. Here's your delta x, and then okay, here's your delta x. All right, and what we are saying here, you look at this. This is fx. Okay, this whole thing here is fx, f of x. Right. So this is what this equation here is saying. dfx dx equals to minus fx over delta x. So this is the initial point, this is the final point. Okay, and this is the delta x right here. Okay, can you see? This is the derivative here, and then we'll have that. We are actually saying that this derivative here is actually this gradient we have right here. Okay, this is this gradient we have right here. Okay, this is the gradient we have right here. Fx and fx is here. This whole bar here is fx. This whole bar here is delta x, and this slope here is the derivative, which is also the gradient. Okay, in that case, they are kind of the same. Okay, so this is actually this equation right here. Alright, where we assume fx plus delta x is approximately 0. But where is this fx plus delta x? Okay, fx plus delta x, right? So this is where we had our first value of x. Maybe you call it x1. Our x2 will be here. Okay, and then we'll have f of x2 right here. Okay, so this is actually not quite 0. This is not quite 0. But it is it's closer to 0 than maybe fx. It should be much closer to 0. Okay, so this is in essence what Newton Raphson method is about. It's sort of using the fact that we can actually get closer and closer. We can get closer and closer to this so-called intersection point where f of x equals to 0, using derivatives to kind of speed up the iteration process. Okay, so I know I probably skipped lots of steps, but the point of this is to sort of get you just kind of revising what the revising what the Newton Raphson method is about, and how it's supposed to get us closer and closer to the intercept point. Okay, and of course the objective of this video is not so much to explain the simple case of Newton Raphson method, I'll leave it to other people to teach you that. But the thing is, yeah, I'm revising you, I'm getting you kind of, or rather I'm also getting myself revised or refreshed. It's just a refresher on what the Newton Raphson method is, and then how can we move from this simple case to something more complicated where we have simultaneous equations. Because this part is for this what do you call that? This graphical thing actually works for one equation kind of a thing where you have y equals f of x. Yeah, but let's say we have multiple equations, how are you going to do the same thing? Okay, so yeah, so let's say we have multiple equations now. Y equals to somewhat. No, it's not just going to be equals to y now, it's multi-dimensional equation. Okay, but if we don't use the y thing anymore, but we still use this thing. Okay, so maybe let's say we have a function 1 and it's a function of x1, x2, okay, and x3. Okay, and this is supposed to equal to 0. Okay, we have a function 2. Okay, x1, x2, x3. So this is 3 equations now. This one we also want to solve for these equations equals to 0. F of 3. Okay, let me get that. F of 3, x1, x2, x... Oh, you know what? I'll probably do this in LaTeX. It's easier. Okay. Okay, multiple equations. Okay, so this is the single equation Newton Raphson method. Okay, so we can keep iterating until we get closer and closer to the actual true 0 point. Yeah, true 0 point. So we repeat the method after we solve for f(x) I plus 1, I plus 1. So I is the iteration number. So pardon me, I didn't actually use all the iteration numbers before. Okay, but essentially we solve for this fi plus 1 equals to fx plus delta x of the last iteration. Okay, I'll just leave this here. I'm not going to correct the nomenclature, but okay. So let's have it extended to more dimensions. Okay, we have it extended to more dimensions. So I'll have 3 equations. Let's say here f1, and this is some function of x1, x2, x3, and this should be equals to 0, right? And then of course I will have 2 other equations because we need 3 equations, 3 unknowns to solve the thing. So assume that this thing can be solved. Okay, we'll have this system of equations that we want to solve. I don't know what functions these are. Okay, but this is just a y equals f of x, the f of x kind of thing. Can we generalize it to a more general case? Okay, yes we can. Okay, we need derivatives. We need partial derivatives as well, or rather derivatives as well. So f1 is a function of x1, x2, and x3. So what do? I need to, again, this is what we want to solve, right? This is what we want to solve, very similar to f of x equals to 0. That's what we want to solve. Okay. If you want to solve the above system of equations. Okay. So we will need to have derivatives of this so that we can do a similar thing that we are doing here. So we're going to do the so-called first order Taylor series approximation as well. And I'm going to do this, right? So instead of doing it for one variable, I'm going to do it for multiple variables here. Okay, df, okay, df equals to f, okay, so df1 equals to f1 at x plus delta x minus f1 at x. Okay, okay, so the same idea here is, say df1 equals to f1 x plus delta x minus f1 of x. Okay, but now we have three what do you call that, three x's down there, three independent variables. We'll need to actually replace this by the following, right? You need to actually put in three coordinates here: x plus delta x, x1 plus delta x1, x2 plus delta x2, x3 plus delta x3. So I actually need to copy these three sets of coordinates over here. Okay, and then on this side I'll have x2 and x3 also. Okay, so this is the first order approximation, so to speak. Okay, first order approximation. So we have f1 and x1 plus delta x1, x2 plus delta x2, x3 plus delta x3. Alright, so we have somewhat of a similar formula here, except we do not divide it by dx just yet. Alright, we'll just have the top part, because there are three variables here. We cannot just do it as and how we like. Okay, now let's expand the left hand side. Okay, let's expand the left hand side, and this will need some partial derivative calculus as well. Okay, so this one I assume you know. I'm not going to do it. So frac partial f1 partial x1 delta x1. Okay, so how are we going to solve for this? Okay, I'm going to repeat this kind of step in 3 dimensions. The total derivative of f1 is the partial derivative of f1 over x1, and then you multiply delta x. You do the same for the delta x1. You do the same for the x2 and x3 as well. So that we can extend this so-called idea to 3 dimensions. Okay, so now we have a very long looking equation, and sooner or later we'll realize why we want to put all of these in matrix form. See, I'm going to substitute this very long side back into df1 here, so that we can have everything in terms of partial derivatives. Okay, so we'll have this very long looking thing here. Okay, and yeah, we don't just need to do it for f1. We need to do it for f2 and f3. So we need to do this for f2 and f3 as well. So what are we supposed to do? Okay, we'll need to just replace all the f1s by f2s and f3s. So that's about 5 f1s we are replacing. So you see everywhere we settle F1, we'll need to replace it by F2, and then we'll need to replace it by F3. So this is the multi-dimension form of the Newton Raphson method. Okay, it's doable, but it's, as you can see, it gets pretty tedious pretty quickly. Okay, so this is the third part. Okay. So once we get this done, I can start writing things in matrix form. Okay, I can start writing things in matrix form. Okay, this part, this 1, 2, and 3 here, I can start writing it in matrix form. So how do I do the matrices here? Well, in LaTeX I have to write matrices like this, so it's a little bit, yeah. So it's a little bit tedious to solve, but okay, we are supposed to separate out the delta x1, delta x2, and delta x3. Okay, let's write this in matrix form. Okay, write this in matrix form, and we'll write. Okay, so I'm going to begin a matrix in B matrix, and this is with the AMS math package. So I have an empty matrix down there. It's not going to really do anything. Okay, so I have just this empty matrix right here. Okay, it's kind of inverted because there's, yeah, I didn't put anything inside, so it's not supposed to make sense at the moment. But okay, we'll need this df1, dx1, df2, or partial f1, partial x1, partial f1, partial x2, partial f1, partial x3 over here, and then yeah, I'm gonna have two matrices, of course, but let's put these partials in there. So it's something like that. I need to put the n sign here, and go to the next line. Okay, so I'll just stuff this equation here and replace the plus with n signs so that we have this in the matrix form. Of course, this is not the final form. We need to take the x1, x2, and x3 out. So I'll take the delta x1, delta x2, and delta x3. I need to take it out also. Okay, so I'm going to delete this, and I'm going to take all of that out. Okay, we'll have this, and then of course I will need to put the second one and the third one. So and now of course we'll need to do matrix multiplication with the delta x1, delta x2, and delta x3. Okay, so let me replace all these f's first, then we will be able to have the the 3x3 matrix here. Okay, this is actually the Jacobian matrix, but don't let them put you off first. This is just a derivative matrix, yeah, but the proper name is called Jacobian. Okay, then let me multiply by another B matrix. Begin B matrix. Okay, and then what do? I need a delta x1, delta x2, delta x3. Oh, and I forgot to close it. I need to close this. Alright, so I've kind of condensed all of this plus things here into these two matrices. So delta x1 will multiply by df1 x1, delta x2 will multiply by this, delta x3 will multiply by this. Same for the second row and this column, third row and this column. This matrix multiplication should not be that difficult. Okay. Right, and then this f1, x1, delta x2, all this will be, of course, put into a matrix as well. I need to put this matrix here. Begin B matrix. Now I'll put the $$ right at the end. So yeah, we'll just take it step by step. Step by step, yes. So F1, F2, and F3. So this matrix actually represents again, yeah, this matrix actually represents these three terms right here. Okay, 1, 2, and 3. These are represented by this matrix right here. Now, of course, we need to have our F1, F2, and F3 matrix. So we're going to do to begin B matrix. We're going to do the same thing for F1, F2, and F3. So let's do F1, F2, and F3. Where's my F1? Yeah. Okay. So there'll be a negative for this. All right. So this is just rewriting we are just rewriting this equation, the df1, df1, blah blah, all of these things on the right hand side, and we are doing it across three. Yeah, we are doing it for f1, f2, and f3 since we have multiple equations. Okay. Okay. Newton Raphson for multiple equations. We are doing this, and then what do we need to do? We actually need to equate this matrix approximately equals to 0. Okay. Again, we need to equate this matrix here, approximately equals to 0. Very much like what we are doing over here. We equate this fx equals to 0. We also need to equate f1 x plus delta x. I mean, all of the things, okay, f1, f2, and f3 approximately equals to 0. Okay, so we are doing that. Okay, begin B matrix. Okay, and I'll just use the 0 vector to do that, to represent that, since we are doing it in matrix and vector form, at least in the engineering sense of the word vector. Yeah, we need to equate or approximate this to 0. Okay, then what happens after that? Okay, what happens after that is that we'll just need to solve for this. Okay. We approximate this to 0, and then we'll just solve this system of equations right here. So it's more of a after this it just becomes a more or less like an eigenvalue. I think the words eigenvalue problem. Never really got those terms right, but more essentially we just solve this equation. Let me put a minus down there. Okay, there's a minus f1, f2, and f3. Okay, so we just have to essentially find the inverse of this Jacobian, or this derivative matrix, which we also call the Jacobian matrix. We need to find the inverse of this, multiply into the right hand side, and then we'll just get delta x1, delta x2, and delta x3 equals to some value, and then we just update our x values accordingly. Okay, so this is how we will solve the matrix. So yeah, the tricky part is of course finding the Jacobian matrix, because this is most of the work, and then finding the inverse. Okay, so that will help us to iterate throughout all these things. Okay, so we shall use the we shall say that this matrix here, okay, I'm going to put this whole matrix right here. We shall say that this matrix right here is called the Jacobian. Okay, and I will use the term vector J to denote this. Okay, so this is a Jacobian matrix. Okay, where is the Jacobian? Yeah, modified nodal analysis. Yeah, see, we have the Jacobian right here, which is this this very complex set of partial derivatives. Where you can see why from this example we have this set of partial derivatives ordered in this manner. We are just rewriting this very complicated equation into something a bit more palatable. Okay, and then we'll just call this thing the Jacobian. That's basically what we are doing. Okay, and of course the idea is to the idea is to find this delta x value. We solve for it, and then we just keep repeating the process over and over again, and this is essentially what Newton Raphson is about. Okay, so the Jacobian matrix is this. We need to find the inverse in order to solve the above equation. Okay, so we find the Jacobian inverse. I don't know if this is the right way to write it, but the concept I want to bring across is this. Yeah, find the Jacobian inverse of Jacobian. Find the Jacobian inverse, and so that we can find our delta x1, delta x2, and delta x3. So delta x1, delta x2, delta x3 is equals to this inverted Jacobian matrix multiplied by the f1, f2, and f3 bits here. Okay, I should take the minus sign out. I'll put it in front. Okay. So yeah, we have the Jacobian inverse here. The Jacobian inverse will be multiplied to the left of both of these equations. And then you'll have this sort of equation right here. Okay, so we want to find delta x1, delta x2, and delta x3. Once we do that, we can get the next step. Once we find this, we can do the next step. Okay, so I can just call this the vector of x. Vector of the delta x, where this vector of delta x equals to this all of these things here. Okay, once we find the vector of delta x, we can update the values, okay, such that vector x I plus 1 equals to vector of x plus vector x plus delta x. So this is the part where we update. Okay, this is the part where we find the next iteration. Okay, so this is essentially what we are doing. Okay, I don't know how we are supposed to get a white vector down here. Let me see if I can find this. Over right arrow. Maybe I'll use over right arrow instead of vector. Okay, over right arrow. Maybe that looks a bit nicer, yeah? Where it basically carries across the message that, yeah, these are vectors. Okay? Again, the syntax may not be the best, may not be what is standard in math, but hopefully it carries across this message of what you're trying to do. Oh, right, I should not have x plus delta x. I just need x down here. Okay, and what is the x? What is this vector x? This vector x is vector x is equals to, okay, I'm going to do the begin B matrix again, and then I'm going to do the first thing is x1, x2, x3. And of course the vector x plus 1 is also something quite similar. Vector x at I. Alright, let me call this vector x at I. x1 of I. Right, I'll do it like that. I do the same thing for the third one. 3i. Okay, now you got it. Now you got it. Okay. So this I is actually the iterations. Okay, this is actually the iterations. So this I plus 1. Okay, so this is the I plus 1 bit. And again, I'll use override arrow just to make things consistent. Okay. Keep substituting until the solution is found within error or tolerance. Okay, keep repeating this thing until your this f1, f2, f3 actually falls close enough to 0 within your set tolerance. Okay, so this is basically what the Newton Raphson method is for multiple equations. At least this is 3 equations. We can actually generalize it to n equations like they do right here. But of course, if you take a look at this, you might be a little bit confused as to what is going on. Now, as for this SpiceSharp, you can see that this thing actually there's some difference in the algorithm right here. Okay. Okay, the Jacobian. Okay. One more thing to note is that the Spice will modify the algorithm a tiny bit. Okay. So this is the way that is normally formulated. That's what we are solving for. Remember that this is our equation here. This is our Jacobian. The Jacobian multiplied by this delta x matrix equals to this thing right here. Yeah. This vector right here, which is this big F of x and the kth iteration. Okay. So the algorithm is modified in the sense that, okay, looks like the Spice algorithm actually makes it explicit in xk plus 1 right here. So this delta x is actually split up into x to the k plus 1 iteration minus x to the k. Alright, splits it up, and then it solves explicitly for xk plus 1. Okay, and then of course the Jacobian is multiplied throughout. The inverse Jacobian is multiplied throughout. Okay, the formulation allows us to immediately calculate the next solution rather than the increment to the next solution, which is this delta x. Okay, so I mean that's the modification for the SPICE algorithm. Okay, so again we just multiply the inverse Jacobian to this side and of course to this side as well. And it says what? The Jacobian right here is called the Y matrix. Okay, so this is the whenever we see Y matrix within the context of SpiceSharp, it refers to the Jacobian, whereas the everything on the right of the equation is called the right hand side vector. Okay, everything to the right of the equation is called the right hand side vector. Okay, so it's yeah, I guess it means is this so-called product, dot product. There's this thing here and the dot product right here. This thing added together is the right hand side vector, RHS vector. This formulation allows us to immediately calculate the next solution rather than the increment to the next solution. Okay, so what's the flow like? Okay, we get this Jacobian matrix thingy set up first, the Y matrix and the RHS vector. We set this up first, then we have a system of equations here. So this is some right hand side vector, this is the Jacobian, this is the 1, 2 and 3. Okay, then immediately we are able to, once we set up the matrices, we should be able to solve appropriately. Okay, and of course the derivatives at a certain point, x, y, z, the derivatives at a certain point, or rather derivatives at a certain x vector, this is actually a constant. Okay, this is a constant with actual numbers, it can be calculated. Alright, you just have to substitute the values accordingly. Okay, so I think that's enough. We've gone through the theory behind Newton Raphson method. I'll stop the video here and I'll see you next video.